welcome everyone at our weekly seminar. Our speaker today is Professor Bożena Czerny, and she will tell us about the accelerated expansion of the universe.
Yes, thank you. So I will start from the outline, because the outline I propose is not quite typical. I will not be talking about my research much or at all, depends on the time, whether it allows or not. But I will start with the summary, because I'm not sure I will ever get to the summary, right? So I think it's a good point to start with the summary. So during the first 2 slides, just 2 slides, please do not ask questions, because summary is a summary. It's my objective or subjective view of the situation. I will go back to those slides again, and then I will start with really step-by-step introduction, how astronomers are really measuring something. So how we are convinced that that the universe indeed expands, and this expansion is accelerated nowadays. So first, the summary. So cosmological constant, which is responsible for this accelerated expansion, is not a new concept. Of course, Einstein introduced that, but theoretically, just for symmetry or generality. But the need for cosmological constant was already stressed by Peebles, who studied the development of the large-scale structure of the universe. He found it difficult to model properly without cosmological constant. Then the measurement of the microwave background from COBE indicated the level of fluctuations which was consistent with flat universe. And if we measure just by eye the amount of material around, this is not enough to fill the universe. And first estimates at the basis of a large-scale structure done by Kaufman, for example, already implied cosmological constant or this content at the level of 0.3, 0.4. Only later.
What are the standard units?
I will go to that. Yes, because no units.
Standard units are no units.
So convincing proofs came later and gave the same value, now 0.7. And I think personally it is really unlikely that the accelerated expansion is a measurement mistake. Now, page 2, still not subject for questions, because this is, the summary. We will return to this slide again at the end of my talk, hopefully. There was a paper, I do not give even a reference here, which 2 years ago stressed that if you use more supernovae 1A, you do not see accelerated expansion of the universe, or at least it's a marginal case. So what they made, it was a plot of the cosmological constant or energy contained with that, and material content, and they had some kind of ellipses, and here there is a division between no acceleration and accelerated expansion, and marginally at 3 sigma they were here. It is really the way to advertise the work, and it's a way to create publicity. Because as I will explain soon later, when supernovae 1A claimed the accelerated expansion of the universe, they had to combine their measurements with COBE. So from COBE, from the microwave background, you have an information that the universe is flat. And from supernovae, you have the kind of ellipse. And then at the cross section, of course, you have small errors. And, oh, sorry, it was. And if you add this kind of flat curve to this plot, this would be going here, then you see that solutions are here in this range, and they are not in the range of no acceleration. So this is the summary. So if somebody understood everything, then this person can go upstairs and do something useful. If not, now I will start. Or fall asleep, yes. And now I will start the section which is subject to any questions. Yes, please ask questions. And I started from just the general statement, how it is in astronomy, because you are a physicist, you have your laboratory, and then you can look around at your subjects from all three sides, whatever directions, and it's simple. In the case of astronomers, we cannot go to quasars or supernovae 1A, whatever. So we can easily measure the position of the object on the sky. This is simple. With the Doppler effect, so with the use of astrophysics, we can use equally easily, the measurement of the radial velocity. Because if we identify some emission lines and those lines are shifted with respect to the laboratory wavelengths, then you can determine the velocity. But the measurement of the distance...
This, of course, is subject to one assumption that the emitter is saying that uncertainty, because we assume that the lines out there and in the past had the same frequency as the lines right now.
This is correct. On the other hand, the light from distant quasars, the line ratios, line separations, etc., they are used actually to confirm that, for example, this alpha parameter, this subtle structure constant is not changing, etc. So actually constraints on change of those parameters is quite also strong from astronomical measurements. Yes, the assumption is there, but then, if you study the line separations, whatever, then you would have to really say that out there everything is just random or arbitrary or whatever. And this measurement is really difficult. I will, here I show the summary of the attempts of the measurement of the Sun-Earth distance from 900 till nowadays. So units here are astronomical units, and now by definition the distance from the Earth to Sun is 1 in those units, and of course we have average. This is a special definition of International Astronomical Union. It is a special average. And nowadays, of course, well, you assume anyway a definition, right? So finally we have an expression of this unit in kilometers or finally in seconds. Yes. Anyway, if we compare here the historical accuracy, you see that we started really very badly because this measurement was by a factor of 20 or more wrong. And only here in the medieval times we started to evolve in the right direction. And
moved outside to
yes, quite a lot, yes.
Those elephants which carry earth, they move slowly.
Mm-hmm. And here, actually, if you want to know this astronomical unit in kilometers, it is here given. So why this measurement was so difficult? Well, some other measurements were actually simpler. So first, if we want to measure any distance in centimeters, whatever, we have to measure something in centimeters. So on the Earth, of course, we can measure the distance. Well, it does not have to be centimeters or kilometers. In the past, it was some other units. Honestly, I don't remember what was used in Greece. Stadium, maybe, yes. Anyway,
that is not unique because
Eratosthenes.
Richard wrote a book about what is the difference between that.
So Eratosthenes was the first to calculate or measure the Earth's radius. How he did that? He knew that there was a well at a place with Cyan. How to pronounce it, I'm not sure. Anyway, some 800 kilometers from Alexandria. And at noon on summer solstice, the light from the sun came just into the well perpendicularly. So he knew that this is the direction to the sun. But at the same day, 800 kilometers away in Alexandria, there was a shadow of a stick. So he could measure the angle between this parallel line and this direction. So he got some 7 degrees, and it is a fraction 1/50 of the whole circle. So knowing this 7 degrees and knowing this distance 800 kilometers, he calculated the circumference of Earth to be about 40,000 kilometers, which is a very reasonable value, right? Very nice. Of course, we are now doing better, but that's not bad, right?
13,000 kilometers.
That's the first step. So
Radius is 7 less than.
This is circumference.
yes, yes. So it's 2 pi times, yes, 60. So it's, I think this is 36, 37, whatever. It's very close. It's very close. It's very nice measurement.
Comment, this number depends upon the definition of the stadium used by these Greeks. There are several of them which differ a little bit. So this number in kilometers is subject to an error.
Well, but probably not huge, right?
Huge, but 10%.
10%, this is not a problem.
Some definition of a stadium will do it twice.
Yes.
Well, but
So once you know this in
yeah,
kilometers,
the unit of stadium was adapted nowadays in order to make it to be a good. That's very simple explanation.
Yeah, anyway, it's not orders of magnitude wrong, right? It's not orders of magnitude wrong. So it is an excellent measurement. And then the next measurement is the measurement of the Earth-Moon distance. This was actually done even earlier, but that was done using the Earth size as a unit. So, and that was another quite accurate measurement. So for this measurement, you have to watch the moon during the possibly longest eclipse, which lasts about 2 hours. And then it takes, so you can see how this eclipse evolves, and you see that the size of the moon is more or less 3 times the size of the shadow of the Earth. So assuming, of course, larger distances, this means that first the moon is more or less 3 times smaller than Earth with respect to the radius. And then if you know that the moon travels around in some 29 days. Then you can calculate this distance as a ratio of those 2 hours divided by 29 days. And then you determine that this distance between Earth and Moon is 1/60 times the Earth's radius. So now if we use the previous measurement, we can get the distance, Earth-Moon distance at 300,000 kilometers, which is more or less correct. Again, quite successful measurement. Now, the measurement which I promised, Sun-Earth measurement. The idea, again, it comes from Aristarchus, and the method is fine. Namely, he observed the moon when only half of the moon was, perfectly half of the moon was illuminated. From the Earth, he observed this moon, so he assumed that in that case, we have the angle, right angle, 90 degrees here in this triangle. Here we have the Sun, Earth, and Moon. So all we need now to measure is this angle, and then we can calculate, and then knowing this distance, we can calculate this distance. So he measured this angle as 87 degrees, and he calculated this distance. But the problem is that this measurement was inaccurate, dramatically inaccurate, because the correct measurement is 89 degrees 5. So this ratio of the Earth's moon to Earth's sun, instead of 1/20, is actually 1/400. So now we have really an error by a factor of 20, right? And this is what was shown on the previous slide. So the measurement of this angle is not realistic. It's not a good way, although formally correct.
So changing only 2 degrees?
Because if it is 90 degrees, then it's infinity. Yes.
Relatively small error causes such a great...
Yes, and of course sun is large, and you have refraction, and you have a lot of effects in the atmosphere, and it was not a good method.
Is this angle 89.5 of a degree, or is it 89 and 51 minutes?
51 minutes, I think.
So it's nearly 10 minutes away from...
Exactly. So he had no chance, and nobody had a chance to measure it. Yes. So this measurement was just a mistake, and actually the measurement which I showed here, when those measurements really converge, those measurements are based on Venus transits. So I will not talk about Venus transits because it's more complicated, but recently there was a Venus transit a few years ago, and many people from many countries attempted again to measure the distance from Earth to Sun, just using the time of the transit. People in Poland, Australia, whatever. So.
But getting better and better results does not make much sense, because the distance is not well defined. The Sun is not round, and it rotates.
But this distance is absolutely critical for the whole astronomy.
But I don't see how you can get as...
It does. Tiny details do not matter. Now now you can measure everything using radar, but I will show you.
No, how can you measure with radar when the Sun first
Well,
has this hot
so you do not measure with respect to the sun, but you can, of course, communicate with satellites around, with, you know,
I'm
so,
worrying about the
yes.
precision of the measurement of the distance to the sun.
Yeah, if they measure the frequency and
What is done is
the
the Doppler
orbits,
and the center of mass being measured, how the sun
Yeah.
respect
Well,
That's different. That's not to the surface, but to the center of mass.
yeah.
I think they measure the
Yeah.
from the orbit. I mean, you have the
But again, the
planets.
center of mass is not.
Yes,
fixed.
but the point is that I think what we want to know the exact parameters of Earth orbits, and not the distance to the sun, right?
Okay, this is a fictitious concept.
And this picture
Square root of the area.
exactly shows why we need this astronomical unit, because then all other distances, at least when we use so-called direct methods, they are measured in the units of this Sun-Earth orbit. Because now, if we look at nearby stars, and we take into account that Earth goes around the Sun, then we see those stars at different positions with respect to the most distant stars, right? So every nearby star performs such a circle on the sky. So we can measure this angle here. This is the so-called geometrical or parallax. And in many cases, we just give the distance. This is the normal way to give the distance. This is in parsecs. This is the distance to the star which performs this kind of motion, and this is 1 arcsecond.
That's why it's called parsec.
Exactly. So you see here the details of the orbit of Earth are not so dramatically important. They are, of course, if you study highly sophisticated systems like, for example, radio pulsars. If you study radio pulsars, yes, you have to make all the corrections for whatever is happening. But if you, with difficulty, measure this thing, then tiny details here.
Is the rotation of the orbit taken into account? Because the orbit is not fixed, but it rotates due to relativistic effect.
In the case of
the 6 months, you don't measure it
No.
in the 6 months.
But if something is of utmost precision,
In the case of radio pulsars, I think yes, they do, because that was the problem with false detection of first planet around neutron star. Before Wolszczan detected his planet, there was a claim detection first by Marek Demiański, and it was not accurate. It was not taking into account some effects of this type. There was another claim, and it was again false because they did not take into account one of the effects.
Yes, there was this infamous case when they claimed to discover pulsar planet, and what they actually did discover is the Earth motion around the sun.
Yes. Yes, yes. But besides radio pulsars, those measurements are not sensitive enough.
So what's wrong with this? Well, it's a very precise way.
So one parsec, by the way, is about 3 light years. So now we are in a quite a lucky situation, because with this distance measurement, this parallax method, geometrical parallax method, we can now go quite far. We cover, well, maybe not quite all galaxy, but significant fraction of the galaxy. So this is the picture symbolically showing the well, Milky Way galaxy. Of course, it's just stretched. Sun is not in the center of the Milky Way. It's more or less peripheric location. And Gaia measurements will go to 10 kiloparsecs. So some measurements are already reported. Data release 2, I think, was today. I didn't check. So at least bright stars will be measured. The distance to all bright stars will be measured in all this volume from Gaia. Yeah.
So it's important to realize that there is one more effect which affects the position of these stars in the skies, and this is something called the aberration. This is due to the fact that the Earth changes its inertial frame, and therefore the apparent position of everything on the sky changes. But this is a slightly different change, and it can be.
But this is all included. I'm not going into details. But anyway, yes, it's really impressive that we are going that far, because at the beginning, traditionally, this method did not take us that far. So now this so-called basic distance ladder is much shorter, because nowadays with this parallax method we go directly to Cepheid stars. This was not possible when I was at the university. So currently there are 15 measurements for Cepheids from HST. Cepheids from Gaia are not yet reported, but they will be, I guess, soon. And if we can have determination of Cepheids, parallactic determination of the distance to several Cepheids, we can calibrate those Cepheids, and we can use so-called Leavitt law, period luminosity relation. So this period luminosity relation was discovered by Henrietta Leavitt long time ago, as you can see. So what are those Cepheid stars? I will not enter into the structure, but those are stars which perform dynamical pulsations because of the opacity in their external layers. So if you look at the luminosity of a star as a function of time, you will see such a characteristic curve. So the star is less bright, then brighter, less bright, then brighter, and it's not symmetric. It's a kind of such a shape. One light curve is not, of course, attractive, but there is this period luminosity relation which was discovered by Henrietta Leavitt. So the point is, if you measure the period from this to this, then you can read the absolute luminosity of the Cepheid. And if you have this relation calibrated quite nicely, then you can measure the distance. So many people still improve this calibration. This plot is showing that this method is really very accurate, because if you compare Cepheids, Milky Way fit to Cepheids, with Cepheids which are in Large Magellanic Cloud, the difference between those two populations is very small. So this method is really quite accurate. and it will be still improving. And then, with nowadays, we go directly from C-fates to supernovae 1A. Again, it was not possible in the past, but now, because we see C-fates in distant galaxies, we can do that. So currently, there are not that many galaxies, but there are 19 galaxies which host both supernova 1A and well-studied C-fates. So now, knowing C-fates, we can calibrate those supernovae 1A stars. So supernovae 1A stars are those outbursting stars. The mechanism is still actually under discussion. So most probably this is the white dwarf Chandrasekhar mass, white dwarf which is accreting from the companion, and then it crosses the Chandrasekhar mass, and because it crosses it, it loses the stability, and then because it happens more or less at the same mass always, then the luminosity of those outbursts are identical. The problem is that it's not as simple as that, and there are still discussions. Those supernovae are also not identical. So here, for example, you see a collection of supernovae light curves, and that one from that one differs by 1 magnitude, which means factor. I always have problems with the factor 2 or something like that. So, on the other hand, you can see that this one, which is fainter, lasts shorter. This is which is really brighter. It takes longer to evolve. So, people invented, a couple of years ago, invented a way how to this stretch and, so you have to observe the supernova. You have to measure the time scale, fading time scale, and then you apply a certain correcting factor, and then you create a kind of a representative uniform supernova. Of course, it is a kind of tricky business. In addition, there has to be made a correction for the host galaxy, because somehow supernovae in elliptical galaxies are different from supernovae in spiral galaxies by more or less 0.1 magnitude. And of course, in the case of very distant supernovae 1A at larger redshifts, then the material has no metals, or in astronomy, everything is metal. Carbon is metal, Helium. Helium is not a metal, right? But everything apart from hydrogen and helium is a metal. And of course, if you change the composition, you would change the properties, probably. Well, since we are not sure what is the mechanism, then. Because they have just one number z, which they change. And this z stands frequently for iron. And then, to make everything simpler, you change iron, but then you change also carbon, oxygen, whatever, and then you have metals.
Maybe it's also because everything else was produced later after the Big Bang. So primarily because it doesn't give you helium and hydrogen abundance. A little bit clear.
No, but I mean, the question is that the word metal is used in physics in a very specific sense. I mean, what differs metal from the other elements on the Mendeleev table is not really the number Z. It's a number of electrons, and what happens with those electrons when there are many of those.
In astronomy.
Otherwise, if you have just one atom of a metal, what's the difference?
In astronomy, one more comment. In astronomy, Z is something else. Sorry, again, misunderstanding. Z in astronomy is amount of everything else which is not hydrogen and helium. Sorry.
So it's like this Earth radius. It's a kind of a number we call this metal.
Yeah, it's just shortcuts. So we have more. Yes.
You better
Yeah.
be careful talking to the chemist, because if they were here, that the phosphorus is a metal or something, they might get a hard.
Well, we know this, but astronomy is the oldest science, so we get to name everything first.
But if you call everything metal, then you have difficulty.
It's just a question.
So having this distance ladder, we can arrive.
But that cannot be completely true in what you said in astronomy, because if you look at the pulsar, that this real definition of a metal we use in the normal Earth physics is important to understand the structure of the pulsar, because you distinguish between the free electrons and the so that was a side comment.
Yeah, it's just.
Which probably exists there as well. But then in this language, metallic hydrogen is not a metal.
Yes.
So now, since we know how to measure the distance even to supernovae 1A, we can, and we know how to measure the velocity, because velocity is just redshift, right? Redshifted lines. We can study observationally the expansion of the universe. And at small distances, this was already done by Edwin Hubble in 1929. So he plotted here the velocity, and here he plotted the distance for several galaxies where he was able to identify Cepheid stars. So this was not yet based on supernovae 1A, of course.
Does one distinguish between gravitational redshift and the Doppler?
It is a Doppler.
But there is also gravitational redshift.
But it's tiny.
It's subtle. It's subtle. In emission lines, you do not see that, because most of the emission lines, for example, in my object, a quasar, emission lines originate at 5,000 gravitational radii. So then gravitational redshift is not important, while kinematic redshift of order of few thousand kilometers per second is easily measured. So this plot.
One comment here. This 1929 was short after Hubble discovered that Milky Way is not the whole universe. It's about 100 years we know that there are other galaxies apart from the Milky Way. This is absolutely amazing.
Yes, that's right, because this, this famous debate whether those other galaxies are inside our galaxy or that was in 1919. That's right. Well, this figure, I think all statisticians say that this figure is not really convincing, and it's not really done carefully, because even units are in kilometers instead of kilometers per second, so it's not really done carefully, but nevertheless, he discovered this. And now we can use supernovae 1A in more or less the same way, so we can plot distance and velocity and have the same kind of diagram. If we measure nearby sources, then this expansion rate is linear, like here, and the slope is given by the so-called Hubble constant. And because if we go to very large redshifts, this would change. Now, customarily, we write this H0. So this is the value which is, let's say, nearby. And nowadays, the velocity relates to the distance through this value, which is more or less 72 kilometers per second per megaparsec. Of course, this is, again, speciality of astronomers to use such strange units, because actually it should be in seconds, right? Because megaparsec and kilometer is more or less the same, but yes, 1/2.
Meters per second is a different unit itself, so just for convenience, yes.
Yes, it is for convenience, right? Because then we can, if we measure the velocity, then we can get the distance immediately in megaparsecs, and this is what we like. So with supernovae 1A, we actually can go to the redshift 2.2 nowadays. Those are the most distant supernovae discovered by Adam Rees. And in that case, we really need a more careful approach to cosmology. So we cannot just use this locally expanding universe. We have to think about the universe as a whole. So now few informations about the universe as a whole and its structure, because we had a discussion a couple of times already whether the universe is uniform or not uniform. So in order to make this discussion quite clear, I first give some the summary of the content. So of course nearby we have stars and planets and their sizes. I gave everything in centimeters, whatever, something like that, quite broad range. Now, those stars and planets predominantly sit in galaxies. There are occasionally, there is, I think, one free-floating planet which is not connected with a star, and there are some stars which are maybe not connected with a galaxy, but that's... So we sit... They were ejected from the system, because if there are binary or triple interaction of stars, one can be ejected from the system. So then there are galaxies, larger entities, and we personally sit in the Milky Way galaxy. The size of galaxies is more or less in this range. Then the galaxies forms groups, and we belong to the local group together with Andromeda Galaxy and several other, I think now close to 100 dwarf galaxies. And then next clusters of galaxies. So we belong to the Virgo cluster, although we are quite distant from the core of the Virgo cluster. Then, still larger sizes, there are superclusters. And we sit in so-called Laniakea supercluster. That name was, I think...
Why do you think we belong to Virgo cluster? What's the belonging definition here? Because I think we're not actually bound to Virgo cluster, we're falling on the Virgo.
But we are falling into it, right? So...
But it's not actually bound, we are not bounded to the Virgo cluster, so... It might still be the case, depending on the dark energy, that we'll never fall into the Virgo cluster because the time space will expand, so... I think it's the definition to belonging to is cartographic, I guess, in this sense. Not
yes, yeah.
What's wrong with cartography?
No, because there is a definition about being bound by gravitational forces. That our binding energy is such that we cannot break from a cluster.
Yeah, but then on the other hand, superclusters are not, I think, bound entities anyway. So this is cartography. On the other hand, you see that on the map, so you give names, and Laniakea is a very nice name, I understand. It was given a couple of years ago. It's not even an old one.
Is there an institution responsible for those names? Like
International Astronomical Union approves some of those. I'm not sure if Laniakea is adopted. Probably not. That's invention of I think, Brantali, right? Who is really enthusiastic of naming everything, because he believes that when we were discovering Earth, we continents, everything, we gave names to those things. So we have to give names to the universe we see. Everything should be.
If something is not named, it does not exist.
yeah, but
Yes.
those names, they like Australia, that's completely ridiculous name.
No, it's a human
Unknown area. It's very well known. Australia, Terra Australia. Nieznana.
Terra incognita.
Nie Australia. Nieznana. Ziemia.
Okay.
Ale jest badana w tej chwili bardzo dobrze.
Okay. So apart from superclusters, which are denser, we have also voids, which are empty spaces, walls, which are more or less 2D structures, filaments, which are 1D structures. So the large-scale structure is quite rich. And now we can define the density contrast, because this is what cosmologists use quite a lot. And the density contrast you can understand easily, for example, taking a circle around a galaxy and then taking a similar circle where there is no galaxy, and you count the content of the material and you calculate the difference between the two divided by the mean, and this is the density contrast.
Of ordinary matter only.
No, of all matter.
All matter.
Yes, all matter.
Including dark.
Yes, including dark matter. Well, if we, for example, if you think about clusters of galaxies, you see that they look like they are gravitationally bound because they are quite spherical. On the other hand, if you count only galaxies, they should not be gravitationally bound. So you know how much mass you have to add to make them marginally gravitationally bound. And this is how you determine the dark matter for the clusters of galaxies. So it's relatively... Yes, but the way I say is simpler, probably.
Dispersion is one of the measurements, right? There's a huge loss of dispersion, and yet the clusters do not disperse, which means they need to be bound.
Yeah, this is what, yeah. So if we introduce such density contrast, we can then start to thinking about typical contrast. So in the case of galaxies, this density contrast is 10 to 6. It's quite a lot. Because, you know, the size of the circle depends now what we draw. If we think about the galaxy, this is why I gave you the size, right? So you have to take a circle of the size of the galaxy from the previous slide, right? We can go to the previous slide. So you have to take a circle of that size, for example, 10 to 22 centimeters for that case. And then to take the same circle, 10 to 22 centimeters, and then you will determine this. If you increase your radius, so now if you go to clusters of galaxies 10 to 25 centimeters, you will draw much larger circle, and you will have galaxy clusters in one place and no galaxy cluster in the other place. But then the density contrast drops by 3 orders of magnitude. It's 10 to 3.
So that's
You see this
the matter is a fluctuation in the universe,
Yes.
right?
Yes. And then if you go to superclusters,
Center of
yeah. If you go to superclusters, so you take the circle of the size of 10 to 26 centimeter, then, then you have this density contrast already a few. So just marginally. No, although not, yeah, I know. It's still not linear.
Is there any scaling law relating to this?
No, because it's highly nonlinear evolution.
If you take a pot with the water and you boil, you have these little bubbles. And there are similar relations, I don't remember the numbers, of the size of the bubbles, the number of the bubbles per unit volume of a boiling water, depending, of course, on the temperature. And there is a beautiful scaling law.
No, there is no such, there is only for small fluctuations, which are 1 or up to a few, you can consider just gravitational instability, and then you can form this kind of a law.
The most important thing is this dark mass, which contributes to this.
There is a scaling law called...
So, does anyone know what...
But then it does not extend to galaxies, I think.
Our mass fraction does extend from the microhalos to the size of the Earth. This is the prediction of the dark matter model.
But then, yeah,
Nearly all sizes, except the sizes larger than the biggest clusters.
If you make an assumption that the universe is full of this dark matter, right? And it has density fluctuation, because it's sensible to assume that if this is a complicated system, it fluctuates, right? Then it, of course, has a certain statistics of those fluctuations.
It's called power spectrum. It's called horizontal spectrum from inflation, which
Yeah.
is scale-free power spectrum, nearly scale-free. So you can expect there's a uniform power on all scales.
And yes, there's
So that should explain this number.
I think it does, yes.
so there's
That
two
was my
numbers.
question.
I don't think at this point you already need cooling. I think for galaxies you need cooling, and this is where this,
Evolution is linear. I'm
yes.
about something just primordial fluctuations, yes.
So those primordial fluctuations we see only in the cosmic microwave background, where those fluctuations, those density contrasts are at the level of 10 to minus 5, more or less. So when we look at in the deep past, because in astronomy we look back in the past and we look at to large distances, more or less at the same time. It's a kind of combined, but still at distances more or less larger than 10 to 27. This universe, those density contrasts would be of below 1, right? And if you go to the past, then indeed those density contrasts are very small.
But these huge differences show that dark matter is not distributed evenly. It cannot be. It must
Dark matter, no.
Yeah.
Dark matter, no. Dark energy is a different thing. But dark matter, no. It forms halos around galaxies, yes.
So all these speculations that dark matter is Higgs or something that would be evenly distributed are wrong. Do not agree with this.
No, well, those Higgs particles would also gravitationally interact with the rest and with each other, so they will form gravitational clumps, right? Yes, so they do cluster. Gravitationally, yes, they do. So now if we think that the universe, at least at very, yeah, should I finish it? Well, I can finish at any moment. This is what I...
Particularly, it was already summer.
This was exactly my reason. So any moment you are bored, you can tell me stop. Stop telling. Okay. Anyway, so at large distances, and particularly in the past, indeed we can say that universe is uniform. We can neglect those small fluctuations, but then we always have to remember about taking large volumes as units for computations. And in that case, Einstein equations reduce to two simple equations for evolving universe, which is isotropic and uniform. And this equation looks more or less like energy conservation. Here, this cosmological constant, lambda of Einstein, is already introduced. And this k is the factor which is related to the curvature of the universe. So if the universe is flat, this is 0, and we don't have this term. This is a kind of dynamical equation. R, of course, is the scaling factor of the universe. So R with dot is the expansion rate, but R with two dots, second derivative, is the acceleration or deceleration. So if
this constant density, right?
this no, this is the density, and it is not constant. This is the density of the...
Not constant in time, but constant in space.
Yeah, constant in space, but not in time. This is a function of time, right?
So this is not the closed equation.
So this is only... Yeah, so this is only the equation which applies to early universe, right? And later you have to do it numerically, right?
Yeah,
and of course...
Whatever it applies to. I mean, you need to know how the rod changes in order equation of state.
Yeah.
If you disregard the pressure, you take
this is usually 0 in our epoch, so this does not count. Anyway, why I'm showing this equation is that to have accelerated expansion, you need this larger 0. And here you have a cosmological constant, and here you have the density of the matter. Pressure nowadays is unimportant, so you can neglect that. But you see that small lambda is not enough to get accelerated expansion of the universe. You have to balance those two terms, right? So you need large cosmological constant to balance the density, to balance the gravitational attraction of the material.
Large means what in 1/meter squared?
Well, we usually do not use those units, so I will go.
What would be, because curvature is in 1/meter squared, so lambda is also 1/meter squared.
No, it's from the, because
No.
it must be equal to the left-hand side.
Yes.
That is 1/second squared.
But C is 1. So
Yeah, well, then time is 0.
Yeah, anyway, those, yeah. So in cosmology, we usually use different units, right? This is what I was showing on the plot at the beginning. So first we defined two quantities which can be measured. This is this Hubble constant, which now can be formally expressed as the derivative of the scaling factor to the value of the scaling factor at present, right? In general, this would be the function of time. And Q0 is the deceleration parameter if we, yeah. And to have a closed universe, we need, and if we have no cosmological constant, we need a special relation between the density and the Hubble constant at present. So we introduce this critical density, which is at present. In the past, of course, then this will also change. And now we normalize the content of the universe to this critical density. And this is how we get the relation that the contribution of the omega matter and omega lambda and omega curvature is equal 1. This is our total budget. But what we see, of course, if we plot this content of the universe nowadays this dark energy dominates. Cosmological constant is constant, right? But of course, here, this is not just cosmological constant. This is cosmological constant divided by the critical density, which is a function of time. So as a result, you see, well, during the recombination epoch, where we observe the cosmic microwave background, we do not see dark energy here. We see more dark matter than nowadays and more normal matter. Yeah. So this is how we see this microwave background in different instruments. This was the first discovery of those fluctuations, which I mentioned, 10 to minus 5. This is WMAP, this is Planck with far more precision. And the picture shows frozen adiabatic perturbations at that epoch when photons decoupled from the matter. So observing this, we can also model the universe. And this modeling does not require this distance ladder, which I was talking about. This is absolutely different method. And you observe the sky, you do the decomposition into multiple moments, and you have to fit with your Friedmann model this kind of curve, and now it's really impressive. I mean, there are problems here with low multiples, but here this fit is an excellent fit. And this actually shows that the universe is really flat. This is what I was showing on the first plot. So this more or less gives you the constraint that omega k is equal 0 and omega matter plus omega lambda is equal 1. And this is how this plot on the introductory or summary slide was created, because as I said, cosmic microwave background measurements indicate flat universe. On the other hand, supernovae 1A measurements are mostly sensitive to the current expansion rate of the universe. So they are mostly sensitive to the difference between omega matter and omega lambda. So this measurement is degenerate, but in different direction. And those two measurements are absolutely independent, and they are both needed. So when supernovae 1A people reported their discovery, they of course combined their results with this. Otherwise,
at least in principle, right? Because they need to assume, for example, general relativity at its core. So
yes, that's right. But
do you know by any chance what is the mass that one would get from the density if we use as a scale of the distance the cosmological constant? Then you get certain mass. And what that would be in kilograms?
A lot.
No.
I don't know. I never did this kind of exercise, but
0.6 times 10 to minus 27 kilograms per cubic meter, roughly.
No,
so this
in kilograms. What is this mass that comes from this simple calculation?
because then the size counts. I think it's horizon, because then the horizon enters. Yeah.
We have a density. Density is kilogram per square, and volume can be measured in units of cosmological constants.
Yeah, and this volume is to the horizon of the universe, more or less. So this is,
Cosmological constant.
but this would be more or less the same, probably.
Of 4. 3 halves. Because cosmological constant is squared. 1 over squared meter. Okay. Well, that's, of course, is a complication.
So I didn't do this exercise. I can do it. I don't think I can do it now, but
Displacement. You get
yes.
some number in kilograms. There are lots of numbers. No, but this is one which says something about.
So just short summary, there are also shortcuts through this ladder. So there are independent measurements. For example, water maser. But I don't think I have time to enter into those details. And of course, in this supernova 1A, you can see that here there are different cosmological models, and those differences, when you use just supernovae 1A, of course, is not so. The error at the level of 50% in flux estimate is a problem if you don't combine the supernova 1A with CMB. On the other hand, I don't think that this conclusion about accelerated expansion of the universe can be avoided. There are, of course, still new methods. I'm working on quasar method, and those methods, I don't think they are needed to confirm the accelerated expansion, but they are absolutely crucial for the discussion of the changes of the cosmological constant with time, because then we are really biased, by the errors which are in the method. Statistical errors are going down, but systematic errors are really difficult to dump, and this is why those methods are really needed, and most of those methods really does not need this distance cosmic ladder, and I just wanted to mention that in the past, when parallax was going only up to this place, now we are going there. I would have to tell you about all those other things. Now I did not. Okay.
One question. Yes. So finally, that's the acceleration. Is there or not?
In my opinion, yes.
Increases or not? I mean, that one.
At least now, I think we are in this phase of accelerated expansion, because this non-accelerated expansion would mean we are going somewhere here. In my opinion, there is no way we would be there with our present knowledge of the universe content, element creation. There are a lot of other things which I had no time to touch.
Obviously, of course, that was a very broad topic. A very quick question. You mentioned at the early stages that with supernovae you can go as far, maybe at redshift 2, which is already, as you know, stretching because of the systematics effects. And at the same time, we know that we need to measure the expansion rate or all possible times, and more the better, because if we want to distinguish the physics from simple lambda from different options, this is the kind of measure we need.
Yes.
So can you give a comment what kind of a redshift we can cover with the method with quasars? Put aside the moment the error. Let's say what can we expect, or what kind of period of acceleration?
Well, as for the error which is in the method, we cannot yet tell, because those methods are in preliminary really developments. I guess, well, from reverberation, a single quasar should give the accuracy of a single supernova, 1A.
And we
So
can observe-
0.1
But you
magnitude.
can observe quasars up to much farther redshift.
Yes,
right? So this
yes,
is-
that's right. On the other hand, I have also nearby AGN. So this covers in a uniform way both low redshifts and high redshifts. This is the problem for example, for the method based on gamma bursts, because they cover only large distances, large redshifts, and then the degeneracy is stronger, and they need calibration and a lot of
Still
other
before.
things. Yeah.
Just to answer the question of Professor Bureau, I think your answer is 10 to 22, but in solar masses. I don't remember how solar masses translate quickly to kilograms.
10 to 30.
Okay, so it's 10 to 50, so 3 in kilograms. The mass associated with the lambda. Just
Okay.
pi by I, very quick.
Uh-huh.
So it is still small
Yes, it's still small.
when you express in kilograms. So it should be compared with masses of elementary particles.
Probably, yes.
Maybe one can get the mass of the proton. So
You are right.
hydrogen atom.
Okay, not attached.
Okay. No. Okay. Thank you.